Okay, good afternoon. So welcome to attending this afternoon cosmological session. And today, this is our first speaker in this session. Speaker is Professor Zhong-Zhi Xianyu, and he is from Tsinghua University. He will talk about family tree and decomposition of the cosmology correlators. Let's welcome.
Okay, great. So good afternoon. First, let me thank the speaker, thank the organizer for giving me this opportunity, and also for all of you being here at the most sleepy time of the day, listening to a super technical talk. Since this is BIMSA, a mathematical center, I indulge myself to include a lot of mathematical and very technical slides. So I warn you, I will bore you with a lot of integrals, but I promise you there's a lot of fun. So the topic of my talk is family tree decomposition of cosmological correlators. I'm Zhong-Zhi Xianyu from Tsinghua. And this talk is based on several papers we wrote in recent years with several of my PhD students. Actually, last year I gave a similar talk here, talking about a similar topic, but mostly focused on this group of papers. So today I will result by including more works from this year, these blue ones. So this is the outline. I will first tell you the background of the whole thing, which is so-called cosmological collider physics. I will introduce the basic idea, and also what is the so-called cosmological collider signals. So what is the signal we are after? And I will put an emphasis on the particle phenomenology, showing you there are actually well-motivated particle physics that give you large signals that we can look for in the future. And all the technical things underlying these signals, these cosmological collider signals, are so-called cosmological correlation functions, or cosmological correlators for short. This is the most technical part one. I will introduce the basic structure, why these objects are important to study, and why they are difficult. And I put an emphasis on recent analytical methods we developed, trying to get exact, precise result of these signals. And in this calculation, a representation, so-called partial Mellin bands, turns out to be very useful. I will introduce a little bit. And the core part of my talk is so-called family tree decomposition. This is essentially a method to deal with arbitrarily nested integrals, time ordering integrals. And I will show you how to perform analytically all such integrals. And in this way, how can we discover a lot of new mathematical structures? And finally, I will put this method in use to get analytical result for arbitrary tree-level correlation functions for a particular toy model, which I call conformal amplitudes in arbitrary power law FRW universe. So that's the plan. Since we do not have many people, so just please break me at any time if you have questions. Let me still begin with this picture I'm sure many of you have seen before. This is a so-called cosmological collider program. Here I am plotting a circle here. The left part is the cross-section of Atlas at the Large Hadron Collider. This is the most powerful collider experiment our humankind have been able to build on the Earth. And it operates at an energy scale of 10 to the 4th GeV, roughly here. And as people working on theory, high energy theory, we also know that there's a holy grail for high energy physicists, which is the 10 to the 18 GeV, where the quantum gravity is supposed to be strong. So if you really want to understand quantum gravity, you want to understand the quantum nature of space-time, then this is the natural place you should look for. But there's a huge gap here, of course, and we are making progress. If we really work hard and making progress in the next 5 decades, probably we will be able to go 1 order of magnitude. Then it's a simple linear extrapolation. for you to see how many years it takes to go to the M Planck. If you do not want to wait that long, then there will be an alternative, which is called inflation. So Sasaki-san this morning has gave a fantastic talk about cosmic inflation, so that I do not need to introduce what is cosmic inflation. But very naturally, we believe that the inflation happens at energy scale probably around 10 to the 14th GeV. So it's here. So naturally, we want to make use of this energy to look for high energy new physics. And the machinery to this is so-called cosmological collider physics, which is the right half of this circle. So on the right part, I'm deliberately plotting the cosmic history in a layered structure. So we have a lot of observables from cosmic microwave background to dark ages and to recent large-scale structure surveys. So the idea is to make use of all this data, all this measurement, the correlation functions of all these fluctuations to infer the information that was happening during the inflation, the 10 to the 14th GeV. So this is very similar to the idea of a collider experiment. Now, what are the signals we are looking for? The signals are the quantum fluctuations of heavy particles that are spontaneously created during inflation. So I don't need to introduce what is inflation, but I want to show you in this Penrose diagram, inflation is nearly exponential patch of this whole global de Sitter. And the physical process we are looking for is the spontaneous pair production of heavy particles, here represented by the red lines. You can think of this just like Schrödinger pair production of charged particle in a very strong electric field. Of course, in the early universe, there's no electric field, but we have a very strong gravity background. The space-time is expanding exponentially fast, and we will be able to make use of this fast expansion to create particles with mass comparable or even beyond the Hubble scale, 10 to the 14th GeV. So this is the engine for the cosmological collider. After the production, this particle will quickly dilute it or decay so that we will have no chance to observe this particle directly. But most likely, these particles will be interacting with infraton mode, the scalar mode or tensor mode, at least through gravity. So we believe there are processes that couple the heavy particles created during inflation to the scalar mode, here the blue lines, that survive the cosmic inflation and that we observed in the either CMB sky or large scale structure sky. So that's the idea. We measure the temperature fluctuations of CMB, we measure the large scale structure, try to measure the correlation functions and infer the existence of this heavy particle. Now, if you do this exercise for a particular process, in this case, a 4-point function, a 4-point correlator, and go to a special limit, which I call squeezed limit, meaning that the momentum transferred in this red line is much smaller than the other 4, then you will see a characteristic pattern created by this heavy particle. Overall, the shape is given by this black line, but you can recognize a smooth background in blue and the oscillatory signal in red. Essentially, this oscillation is a consequence of the oscillation of the field, the wave function of the heavy particle interacting with the inflaton. So there's a resonance happening between the inflaton and the heavy particle, and this resonance will translate the oscillations of the heavy field to the oscillations in the correlation functions. So that's the idea. So by measuring these oscillations, you will be able to extract a lot of physical information, including the mass, the spin, the angular momentum, interaction type of these heavy particles. And why am I talking about cosmological collider physics now? Given that we haven't seen any non-Gaussianities, any positive detections of this 4-point correlation function or 3-point correlation functions now, because we will be making progress in the future. So here is a prediction from the SNOWMAP study several years ago, predicting that there are actually quite a few large-scale structure survey experiments that can push the sensitivity of detecting non-Gaussianity by 1 or 2 orders of magnitude in the near future, next decade. So we do want to make use of this opportunity to look for fundamental physics at 10 to the 14th GeV. Actually, I want to mention 2 papers appeared very recently where they actually already make use of existing data of CMB and LSS to extract signals of oscillations. And in this paper, they even claim a 2 sigma detection of oscillations. Sure. Is a predicted sensitivity of FNL for the local FNL. Yeah, currently it's like 5-ish by Planck. And the target for example, this sphere X experiment down to 0.2. And the sphere X is supposed to be launched maybe this year or next year. So it's like 1 order of magnitude. Okay. Yeah, represent. Yeah, I think the black one is existing data, and this gray one is a proposed one. And this even lighter gray, maybe just a PPT work. Yeah. I'm not sure for the detail, but roughly. Okay, this is what I said. The oscillations in these correlation functions actually contain rich physics, because if you look at mathematical expressions, if I write down this correlation function as a function of momentum transferred in this heavy line, and I do a Taylor expansion around Ks equal to 0, you will recognize pieces. One I call S, and this S is multiplied with a complex power. As complex power, you know, this is a non-analytic function. It's non-analytic. And this complex power also tells you that in the real space, you will have these oscillations. You will see these oscillations. Because complex powers, if you take complex conjugate and take the sum, this is nothing but sine log, right? So this is logarithmic oscillations. So this is a cosmological collider signal. On the other hand, there's a totally analytic piece, which I call B. This is a background, the smooth part. So in principle, both S and B can be measured by experiment. And these are arbitrary functions. So you can imagine a lot of things can be learned by the shape of this function, just like a lot of physics can be learned from the gravitational waveform of binary mergers. This is what I said, particle mass, spin interactions, and so on. But in this talk, I want to emphasize another aspect of the signal. That is, the oscillations of this complex power is very closely tied to the analytical properties of amplitude. What do I mean? I mean that if you plot this oscillations, complex power, on the complex plane of momentum, then it becomes a branch cut on the negative real axis. Right, this is complex powers. This is actually very similar to what happens in flat space-time. In flat space-time, if you look for a new particle, say a Higgs field, Higgs particle, you look for a bump, right? Why it is a bump? Because if you look at the complex plane, the on-shell production of a Higgs actually provide you a pole very close to the physical region. So that if you search the data in the physical region, the pole will manifest itself as a bump. This is a flat space story. Now you go to the inflation, the expanding space-time, where you do not have stable particles due to the cosmic expansion. You have only unstable particles. So as a result, you do not have poles, but branch cut. Then this branch cut will manifest itself in the physical region as this logarithmic oscillations, which is nothing but cosmological collider signals. So this relation between the analyticity and the signals tells us that it's important to understand the analytical properties of cosmological correlators. And we developed quite a few techniques called factorization theorem and cutting rules to deal with this. I will mention later. Another aspect of the story is the particle phenol. Actually, in past decades, we have been working very hard trying to identify natural particle physics that will give you visibly large cosmological signals. By natural models, I mean to produce signals with reasonable magnitude in a natural way. Natural means we do not tune any parameter. If you just tune parameter, you can tune any signal large, no problem. But if you do not tune, and it's actually not easy, it's actually very non-trivial to get large signals. But still, we are able to identify quite a few particle scenarios where you do have large signals, already shown here, very busy plot. Horizontal axis is the frequency of the oscillations. The frequency is a dimensionless number, which shows you the mass of the particle in the unit of Hubble. And the y-axis is a signal strength. So the shaded region is the region where you can probe in the future, and you can probe a lot of scenarios here. Now, the real thing, the particle process underlying these signals are Feynman diagram shown here. These are simple Feynman diagram, tree level, one loop level, simple in the quotation mark because these are Feynman diagrams in curved space-time. You have to take into account the effect of space-time expansion. So this is actually quite non-trivial. Take this very simple example, the tree-level exchange of a single scalar massive particle as an example. If you have ever had a quantum field theory course, you can get the result of this amplitude in seconds, right? This is nothing but propagators multiplied by vertices, propagators being 1 over p squared plus m squared. Very simple. But the analytical answer for the same process in de Sitter was not known until 2018 by a group of people, including Nima Akani-Hamid and friends working on cosmological bootstrap technique. And the result is expressed in terms of complex combinations of hypergeometric functions. So it's much more complicated. However, it's very important to get precise and efficient way to compute this diagram. Because in the future, if you really want to measure these signals, you want to handle a decent set of templates to observers. And you must be able to compute these diagrams efficiently and precisely. So that requires us to understand the amplitude better than we are now. So by understanding the amplitude, I mean two things. First is to efficiently calculate these correlation functions, either analytically or numerically. Another aspect is analytical structure, as I already showed. The relation between the signals and the branch cut structure is very important for us to understand this correlation function. And more broadly, whenever you see some non-analytical behavior in the correlation functions, it means something. It means something physical is happening. So that's the whole motivation for my talk. We will be able to measure the signals. There are good particle physics motivations for that. So we need to take seriously these correlation functions. So any questions at this moment? Yeah. Yeah, good. Yeah. So the horizontal axis is the mass divided by Hubble. So being order 1-ish number means that this particle have mass around Hubble. Clearly, standard model particles are much lighter. However, that's for today. During inflation, there are multiple ways to correct the mass. Say the back reaction of inflaton of space-time curvature, so that very naturally, the mass of a particle during inflation is actually of order Hubble. including standard model particles. So, for example, in this top quark or Majorana fermion scenario, we mean you couple the standard model particles with an axion-like inflaton field. So that the inflaton will back react to the standard model fermion as a particle source, right? Because inflaton is rolling, this becomes a source which picks up the temporal component, and this term will be proportional to the particle number density. That's why you can have a large signal in this scenario. You can see the back reaction is very important here. Okay, any other questions? If no, I will go to the technical part. So let's take serious the correlation functions. These are gigantic integrals. Take a typical Feynman diagram here, the box diagram, as an example. What we need to compute here is an integral. Of course, over independent loop momentum, for sure, just like in flat space-time. But in addition to that, you also have these time integrals coming from every vertex. This is different from flat space-time because in the inflation, what you calculate is actually the correlation functions, the equal time expectation value of a product of fields. So this observable naturally break a symmetry so that you have to treat space and time separately. So you have no right to do full momentum representation. You have to leave time manifest. And the upshot is that you have to perform time integral over every independent vertex. So you have a lot of time integral and you have momentum integral. And what is being integrating, the integrand here consists of external lines and bulk lines. So typically, the external lines are just massless scalar field or massless mode. These are simple exponential functions, e to I e tau. This is just exponential. The complicated part comes from the bulk line, the internal line. Since we are interested in massive particles, due to the space-time distortion, the mode function of massive field are typically Hankel functions. And here I'm being schematic. By a capital H, I actually mean a product of a lot of Hankel functions. And actually, every internal line will be a product of 2 Hankel functions. So in this example, you will have 8 Hankel functions in the integrand. And to make the things worse, you will have these theta functions ordering the time. Because you are doing explicit time integral, the time ordering matters. So you have to deal with these orderings. So it is clearly very complicated to do the integral directly. So we developed a few techniques in the past few years trying to solve these problems one by one. For example, to deal with the special functions, the Hankel functions in the integrand, we perform the so-called partial Mellin-Barnes, which I will introduce later. Also, for simple loops, we have methods like spectral or dispersion, I will also mention. And to deal with the time ordering, we came up with this so-called family tree decomposition. This is the core part of this talk. And in the meantime, other methods are also being developed, like what I mentioned, the cosmological bootstrap, developed by Akani Hamid and friends. Also the full Mellin space-time approach developed by Slade and friends, and also differential equation techniques. So let me introduce a little bit about this partial Mellin-Barnes. This is the very first technique you need to understand in order to appreciate the family tree decomposition. The idea is actually very simple. We perform Mellin transform. Mellin transform is just a very simple mathematical transform which writes any function as a combination of powers. So this is very similar to the Fourier transform in flat space-time. In flat space-time, we do Fourier transform because there are space and time translation symmetry. In de Sitter, we do not have time translation symmetry, but we do have a dilatation symmetry. So we can do very similar things. We expand everything not in terms of plane waves, but in the eigenmode of dilatation, which is nothing but powers. So this is Mellin transform. And by partial Mellin-Barnes representation, we mean that we do Mellin-Barnes representation for all bulk lines, not external lines. In this way, all the special functions will be reduced to powers. So take Hankel function as an example. This is a special function. You don't have to know the exact form, but this is a special function. But if you take Mellin-Barnes transform, it will be resolved into powers of momentum and time. And very importantly, the momentum dependence and time dependence are factorized. So you can separately study the momentum integral and time integral. So this is the Mellin-Barnes representation. After you're doing this, you realize that the whole integral just gets factorized into a loop integral and a nested time integral. And there are very nice pole structures on this Mellin. Of course, in the end, you have to finish all the integrals. You have to finish these Mellin integrals. But very typically, and you can actually prove in infrared safe theory, the Mellin integrand are meromorphic in the sense that there are only poles, no branch cut, so that you can finish the Mellin integral just by collecting the residues of poles. So the message here is that once you take partial Mellin-Barnes, you can do loop integral and nested time integral separately, and the final layer of Mellin transform, the final layer of Mellin integral can be trivially done by collecting the residue of poles. So that's the idea. And as I said, this pole structure encodes a lot of rich physical information. Take one example. By actually analyzing the pole structure of the integrand very carefully, we are able to prove so-called all-loop factorization theorem and the cutting rule for arbitrary loop diagram. The essence is that if you want to extract only the signal part, not the whole thing, only the signal part, the oscillation of arbitrary loop diagram in the soft limit, in the squeezed limit, you have right to cut open the diagram and compute the left and the right diagram separately, very similar to the on-shell factorization in the flat space-time. And for arbitrary loop, the signal can be computed analytically, and this is the result. And this is some application. If you apply this factorization to one loop process, we are able to compute exactly the signals coming from all possible 4-point function with one loop topology. So I don't want to go to detail here. And you can also make progress if you want to compute the full shape, not just the signal, by making use of this so-called spectral representation. This is very similar to the Kellen-Lehman representation in flat space-time. The idea is that a bubble shape can always be written as a linear superposition of tree-level diagram with different masses. So by finishing this spectral integral, you will be able to get a full analytical answer for this one loop diagram with arbitrary massive exchange. And this is actually the first and currently only known complete analytical result for massive one loop processes. And we are currently also developing new ideas. Actually, this paper already appeared last week using the dispersion relations. The idea is, again, to analyze the pole structure and the branch cut structure on the complex momentum plane. And you can form appropriate dispersion integrals so that you can reconstruct the whole correlation function based on a knowledge of branch cut. So these are the things I want to mention very briefly and save some time to the next part, the family tree. So before going to this detail, any questions? Infrared safe means that the diagram does not diverge in the late time limit. because inflation is exponentially expanding, it's very easy to have infrared divergent integral in the late time limit. Yeah, that's right, that's right. Since I'm always considering massive things, so it's typically safe in the infrared. Okay. Any more questions? If no, let's go to the fun part, which is the family tree decomposition. As I said, if you apply the partial Mellin-Barnes, then in your integral there will be no special functions, only powers and the exponential function, right? So let's just consider the most general integral with arbitrary layer of time, arbitrary time orderings, and typically it looks like this. You have an integral of arbitrary number of vertices. So in this example, capital N time variables, tau, with integrand being arbitrary power functions multiplied by exponential functions. And you can have arbitrary time orderings. And very naturally, every such integral can be represented by a graph. I emphasize this is not Feynman diagram. This is just a graphic representation for this time-ordered integral. Okay, and it is very intuitive. Due to the time ordering theta function, there's a natural idea of time flow. Say in this expression, tau 1 is earlier than 4, 2 earlier than 4, 4 earlier than 3. So very naturally, you have a time flow from 1 to 4, 2 to 4, 4 to 3, right? And to each vertex, I associate 3 variables. One is a time being integrated, tau, very simple. Another is omega, which I call energy. This is nothing but the energy injected into a vertex through external lines. And also I have a twist, Q, which I call twist. It is essentially determined by interaction type and also the space-time expansion. So this is the most general integral I need to consider. And you realize that the difficult part actually comes from this time ordering. If there's no time ordering, the answer is simple. It's just Euler gamma function, right? I suppose you know what is Euler gamma function. Integrate power functions multiplied by exponential, and it's just Euler gamma. So all the complication comes from this time ordering. The thing is that you cannot remove these theta functions, no way. But you have the right to flip the direction of time flow by making use of this trivial identity of theta functions, right? Very simple. This is a key part, the key part of this talk. There's a very simple identity. If you flip the direction of a line, you generate additional factorized part. Factorized means that there's no time ordering. So you will reduce the difficulty. Then what is the family tree decomposition? Family tree decomposition means that whenever you have a nested graph, you flip some direction in the graph such that all nested resulting graphs are partially ordered. Now, what is partially ordered? I can use this terminology to explain everything. In any pair of points nested by a time flow, I can call the earlier side the mother. I call the later side the daughter. Then a partially ordered diagram simply means that a mother can have arbitrary number of daughters, but a daughter must have only one mother. Very simple, right? So in this way, every resulting nested graph can be interpreted as a maternal family tree. A partially ordered graph is just a family tree. That's why we call this family tree decomposition. So here is an example. I have a 5-layer integral with arbitrary nesting structure. I can just do some flipping exercise to organize everything on the right-hand side into a partially ordered structure. And you just think about this for several seconds, you realize that if you decide earliest side, in this example, it's side 1, then you just totally fix the partial order. And you can also do decomposition in a different way. You realize there are a lot of different ways to do this family tree decomposition. Here, just for convenience, I introduce a notation to denote all the family tree integrals. I will not explain this notation, but only show you some examples, very easy to understand. Say, for example, I have one mother. The mother 1 has one daughter 2. 2 has a daughter 3. I just use this 1, 2, 3. But mother 1, if mother 1 has 3 daughters, 2, 3, 4, I just add a parenthesis to enclose these daughters. And if a daughter has her own daughters, I add parentheses to the whole subfamilies. So in this way, all the family tree integrals can be very conveniently written in this way. Now you must have the question, why do I do family tree decomposition? The answer is that once a diagram has an organized partial order structure, I can do the time integral layer by layer. So this is the most technical part. I will skip the detail. The idea is that whenever you do one layer of integral, you generate some special functions, incomplete gamma. And I take partial Mellin-Barnes to this incomplete gamma to get a power function again, so that I can do the next layer integral in exactly the same way. And I go through all the layers, I finish the Mellin-Barnes integral, I get the result. And I can show that the result for arbitrary family tree can be written down in this very compact and simple series expansion. Okay, some examples, like this 3-side integral. If it is a simple chain, 1, 2, 3, then I can expand the whole result into a series, and the expansion parameter being the reciprocal of omega 1. If I do a different family tree decomposition starting from 2, I get a different series expansion with expansion parameter being the reciprocal of omega 2. So you realize all the family trees are actually multivariate hypergeometric series. And it's always expanded in the reciprocal of earliest energy. And the prefactors here, the prefactors with this complex power Q, gives you the monodromy of the whole integral. So these are super complicated series expansion, but for simple family trees with small number of family members, they do sum into known functions. So if there's just one, this is Euler gamma. If it's a two-side integral, it's Gauss hypergeometric function. 3-side is either Appel function or Campbell Fourier function. And with more complicated family trees are not yet named, but they are still valid special functions. So in this way, we discovered a new class of hypergeometric functions. And this slide is showing that we can actually take the flexibility of Mellin-Barnes transformation to get more series expansions. Previously, I'm expanding everything in the reciprocal of the largest energy, but I can also expand in the energy sum of some site. So there's a large number of possibilities to expand the family tree integral in arbitrary ways. The important lesson here is that the flexibility of partial Mellin-Barnes representation leads to many distinct expansion of family trees in terms of either large or small single energy or partial energy or total energy or energy differences. So lots of possible ways to do this. And the different family tree decompositions and expansions of time order integrals yield infinitely many functional identities for these hypergeometric functions. So for example, if you play the flip direction trick to the 2-side integral, you get some functional identities of Gauss hypergeometric functions, which you can find in a good mathematical book. But for more complicated family trees, you can get even more complicated identities, which are likely new result. And I want to emphasize very important part. When this series do not close to the known special mathematical functions, these identities actually amount to analytical continuation beyond the region of convergence. So in this sense, we know how to take analytical continuation when a series expansion no longer converge. This is very important for us to understand a new special function. Yeah, they do. I will mention later. Yeah, good. Yeah, thanks. Actually, you can perform one more layer of decomposition, showing that actually family tree are over complete set of functions. You can actually use the identity of theta functions in a reversed direction. And this shows you that all the branching structure of a tree can be further decomposed into chains. I call this birthday rule because this is nothing but compare the birthdays of all family members and you sum over all possibilities. So if you ever know the polylogs and the shuffle products, this is nothing but taking shuffle products recursively among all family trees. So here is one example. You have a 5-side integral with one branching structure. You do this shuffle product decomposition, you can further reduce this into the sum of chains. And these chains are just standard iterated integral. There are a lot of mathematical structures in such integrals, including the Hopf algebra, so that you can define the concept of transcendental weight to such integrals. And you might wonder whether you can develop useful techniques like symbology for polylogs if you can generalize these techniques to the family trees as well. But in any case, this decomposition shows you that these functions have very high transcendental weight in the sense that these are brand new special functions which cannot be reduced to any known special functions. So you have to study them independently. And our method of flip direction and partial Mellin-Barnes provide you a tool to get series expansion and also the way to analytical continue this series. So this is all for the family tree decomposition. Next, I will go to an application. So any question before I go to the next part? If now I will use the last 15 minutes to talk about a fun application of this method, which is a conformal amplitude in arbitrary FRW universe. I have to say this is not a realistic model. This does not describe the real cosmology, but only a toy model. But this is a very important toy model. I would say this model to cosmology is like lambda phi 4 to usual quantum field theory. You understand this model, you understand a lot of things. So the model is actually very simple. It's just a massless scalar field phi, but non-minimally coupled to the Ricci scalar field. You tune the coupling to a value dependent on the dimension, and you will have an enhanced symmetry in the quadratic part, which is essentially a wild scaling. That's why we call this conformal scalar. The whole thing enjoy enlarged conformal symmetry. But this is trivial. This is trivial. To make things a little bit non-trivial, I add polynomial interactions, arbitrary polynomial self-interactions of this conformal scalar field. Then by performing a conformal transform, you can show that the whole thing can be reduced to a massless scalar field in flat spacetime, in Minkowski spacetime, but with time-dependent couplings. And time-dependent is fully captured by these power functions in time. So this is a model. And the simplicity of this model lies on the fact that the model function is just an exponential function. Okay, just plain waves. There are a lot of activities in recent years from the amplitude community studying this model. And the earliest result is the cosmopolitals developed by Nima Akanihame and friends. Using this polytope recursion relation, they are able to derive the integrand for all the tree level and loop level amplitude. And afterwards, there are a lot of studies exploring the symbol structure, the twisted cohomology, and also the canonical form. The most recent progress from Nima's group is that they came up with a very sophisticated mechanism, algorithm, to write down the arbitrary differential equations satisfied by this diagram. So this answers Sasaki-san's equation. Actually, you can derive the differential equations for these integrals. But after seconds of thought, you realize that the whole thing, the tree level amplitude for arbitrary conformal scalar, is nothing but family trees. Because you are just doing integration over exponential functions multiplied by powers. So with the family tree technique, you can actually directly find the full analytical answers without writing down any differential equations. I want to emphasize this is important because if you go to the differential equation work, you realize that the number of equations increases exponentially of vertices. So if you consider a four-side diagram, it is a total of 64 equations, 64 coupled differential equations. Very difficult to solve, if not impossible. But with this family tree, it's very easy to write down the answer directly. Yeah, this is just a frame transform. Frame transform. Yeah, just a conformal transform. Yeah. It's the same. It's the same scalar. Yeah. Well, we'll skip this one. Okay, so let me clarify one thing. There are actually two types of amplitudes when I mention cosmological amplitudes. So I mean either the correlation function or the wave function coefficient. These are technical terms I will not explain. I just want to tell you that they are conceptually two different things, but they are technically very similar to each other. You have the same technical tool to deal with both stuff. So I collectively call them amplitudes. Take wave function coefficient as an example. The Feynman rule is this. For every bulk line, for every internal line, you have these propagators in terms of power, in terms of these exponential functions with time orderings. And each vertex, each boundary line is just a simple exponential functions. And you'll realize for each vertex, only total external energy is relevant because the boundary line enjoys these simple identities. So that if I want to specify a diagram for a wave function, what I really need to specify is the energy injected in every vertex and the energy or momentum flowed in each internal line. And so I will call this vertex energy and K the internal energy. And then the idea of computing this amplitude is just trying to find a way to decompose everything into family tree integrals. And here is the algorithm. The idea is that you just fix a partial order. You just fix the partial order in arbitrary way, and you write down the uncut part. So here's a little bit more complication compared to my original notation for the family tree. I add some subscript here, which simply means that I add or subtract appropriate internal energies to the X energy. And in this way, I can get the most nested part of the result. Then I execute all possible cuts. And I sum over all possible cuts together. I get the final result. Thanks. So it's just the one line stuff. Here are examples. The two-side chain still written in terms of uncut part and cut part, and four-side star similar. As I said, if you write down the equations, this four-side star satisfy a couple equation with 64 equations, but the whole answer, analytical answer, is very simple, just 2 lines. This slide is just to show why the rule is correct. You just do a very careful analysis of Feynman rule. You realize there's a cut structure. So that's why you can prove this rule is correct. And finally, I want to compare our result with the result from Nima's group, since they are working with the energy integral and representation. But essentially, the energy integral representation and our time representation is connected by Fourier transform. So if you just do Fourier transform, you can very easily translate our family tree result to the energy integral so that you can prove that two are actually equivalent. Another very interesting limit is you go to the inflation limit. If you work with amplitude, you know there's a lot of activities recently on this phi cube theory. And in de Sitter phi cube is also very interesting, especially for conformal scalar field. And because this is, in a sense, at the boundary of IR safe region, you nearly have the time divergence, but the divergence will be cancelled in the final result. And this cancellation of infrared divergence is also manifest in this family tree decomposition, because we'll send the limit of Q to 0, which corresponds to the case I'm studying. You'll realize that the finite part is nothing but polylogs. So you realize that all the family tree integrals in this limit reduced polylogs. Here is a more complicated example. Three-side tree will reduce to the third order polylogs. So in a sense, our family tree integrals are direct generalizations of polylogs. So that's all the technical part I want to share with you, but I want to conclude my talk with a few remarks. I mentioned why the analytical computation of this cosmological correlation function are important if you really want to do cosmological collider physics. And since 2022, we actually made a few progress trying to understand this diagram better. Actually, before 2022, the only existing result is this tree-level exchange of single massive scalar field. And in these 2 years, we are able to develop more techniques, including the partial Mellin barns, the improved bootstrap, also this family tree decomposition, and also the spectral method. Also, we proved the factorization theorem and cutting rule, so that nowadays we can compute correlation functions with many different complicated topologies. And these analytical results are important for us because they enable fast numerical implementation. For example, we did the exercise for a brute force numerical computation for a one-loop diagram here. It takes like 10 to the 5th CPU hours. So 1 week, a huge cluster. But nowadays, with this analytical result, we can do this on a laptop in seconds. So this is very important if you really want to make efficient template for future observations. Of course, we are far from done. Currently, we are able to do arbitrary massive tree diagram in the sense that we trivialize the whole problem into a mechanical procedure. Whenever you have such a tree diagram, you do partial Mellin barns, you do family tree decomposition, and you are done. Also, if you're only concerned with the signals, then the non-local signals in arbitrary graphs at the all loop orders are obtained thanks to a very careful analysis of pole structures on the Mellin integrand. Also, we identify a new class of special functions, which we call family trees. And we discover a lot of new mathematical structures like Hopf algebra and symbology. And we want to explore this further in the future. And as a simple application, we obtained a full analytical answer for the conformal amplitudes in arbitrary power law FRW universe. So this is a good toy model, and we learn many lessons from it. And currently, we are also trying to think about new things to do, like one loop bubble has already been done, but other simple loops should be doable as well to get a full shape. And currently we have a theorem to prove the analytical result for these non-local signals. But there are also a more subtle type of signal which is called local signals, which is not even defined for arbitrary loop diagram. We are currently working on that. Also, analyticity of arbitrary graphs is very important if you want to develop dispersion techniques. Also, our universe is not exactly de Sitter, so it's important to go beyond exact de Sitter limit, like to including slow roll correction, and also to consider cosmological collider physics in non-inflation scenarios. And finally, but not least importantly, the analytical result inspired template design is very important. If you eventually want to talk to observations, you really need to make very efficient template. And we believe that these analytical techniques will be very important. So in one sentence, we believe we discover a very rich mathematical structure underlying the deep physics of quantum field theory in cosmological background. That's all I want to share with you. Thank you.
Okay, thank you, Professor Xianyu, to give us this nice talk. Any questions?
So probably it's related to this beyond the star, but so in general, or maybe we think, or I think, that there may be some, say phase transition or phase changes depends on the value of a, say, inflaton field, or maybe inflaton is actually multi-field and so forth.
Sure.
In that case, you may have even more sort of complicated structure.
Yeah.
So, for example, if you had some kind of, say, phase transition type thing during inflation, such a thing can you, at least at the current level, is there a way to include such effects?
That would be very difficult. But the good thing is that the phase transition, if ever happened during inflation, likely to happen at a smaller scale, because you have to take care of all the CMB observations.
Right. Yeah. Sure. Oh, okay. At least at the CMB scale, it shouldn't happen.
Yeah.
But on somewhere at the smaller, a little bit smaller scale, if they say transition, say the energy scale between these before and after is small enough, let's say, in that sort of, maybe you could do some perturbation of the one star to the other star, for example.
Sure.
Do you think you can treat such cases?
That would be much more complicated because the loss of a lot of symmetries.
Maybe for some simple graphs.
But I want to make a comment that this partial non-invariance is actually very flexible. It does not rely on any symmetry, except the space-time translation symmetry and translation and rotation. So if you do not have time translation, say you have a phase translation, as long as you have an analytical approximation to the mode function, you can still perform this non-invariance. And you can still do,
Again, in that case, at least you have, well, you do need some kind of UV cutoff pops, but you do have analytical function.
Sure, yeah.
Okay. If there are no questions, let's welcome the speaker again. And we will back at 2:15. 15, sorry.